So we're going to look at finding the variance and standard deviation. And really they are very similar processes. In your book, they've given you formulas for the population variance and the sample variance. Now, the formulas really only differ on the denominator, okay? And the only major difference is for a sample. We talk about the total number of data, subtract 1 is what we'll divide by. With a population, we divide by the total number of data. Now, they use different symbols. Now, I've given this V because this is the variance, but if you'll notice the standard deviation of these two things are almost identical. The only difference is over here we have squared, okay? And here this stands for the standard deviation, and all we're doing is rooting the other side of the equation, okay? So this symbol here stands for the sum of. So we have to add up all of the values. So we take each set of data that we have and we subtract it from, in population, this symbol here stands for the mean. Okay, I'm going to write that down. So this symbol with a population stands for mean. And I think it's called mu in the Greek alphabet. This is x bar. This stands for the mean in a sample. So really they stand and are sitting in the exact same spot. This would be the mean and this would be the mean. Okay, we have to square all of that information, sum it all together, and divide by the total number of data. We do the exact same thing for a sample. The difference is a sample is where they give us, so many sets of data. Where in a population, we're using our information to represent an entire population, so there is a large amount of data. And a lot of times when they talk about population, they've usually already given you a mean and a total number of interviews. They wouldn't usually get you to solve an entire question like that because there's so much data involved to represent an entire population of something. Where a sample can be, anything from 5 to 500 pieces of data. Okay, processes are almost identical. And you'll see the standard deviation, exact same thing. This is the mean, and all we're doing is rooting it at the end, and that will give us our standard deviation. And we're going to go through this process to find the standard deviation. Okay, this Z stands for the Z score. I should have talked about that also. Each piece of data you can get something called a Z score for it. And eventually you'll start to look up Z scores on a chart, and it'll make a little more sense to you. But we're just going to look up how to use standard deviation and variance to get a raw Z score. And the raw Z score, same thing as you take the piece of data and subtract it from the mean. So here we're clearly talking about a sample divided by standard deviation. And they use S to represent standard deviation of a sample, and they use theta to represent standard deviation of a population. So that's the differences between the two. Okay? A lot of info there. Convert to raw Z scores. Oh, I forgot to write the numbers down. That would have been nice. Okay, 18, 15, 26, 20, and 21. Okay, so we have 1, 2, 3, 4, 5 pieces of data. Now, this is considered a sample. Okay, we have 5 pieces of data, and this is a sample of all the data. We're going to actually have to find, and let's write out our formula here. Standard deviation, we find the square root of the sum, and then we take this x stands for each piece of the data. So for every single one of these, we're going to be filling it in, and we're going to be subtracting from x bar, which represents the mean, and we're going to square them all, divided by our n minus 1. Now, the one piece of information we really don't have right now is we know n. What is n in this case? Yeah, we have 5 pieces of data. So we know n, and we do know each piece of data, the x. We don't know x bar. And what is x bar? The mean. So in order to find the mean, we have to sum all of the data. So you could kind of write it like this as a formula. The sum of our data divided by the total amount of data. Right? So let's sum up all of our data. We have the values of 18 plus 15 plus 26 plus 20 plus 21. Oh, very convenient. X bar in this case ends up being, we'll say x bar is equal to 100. Okay, so our mean is of course it's not 100. What did we forget to do there? Or what did I forget to do? Divide by 5, which means it's 20. What to say? That doesn't make sense for a mean. 20. Scratch that out. Okay, so our x bar is 20 in this case. So an easy way to sometimes do this, I'm going to zoom in a bit, is to create a type of chart, and we kind of tend to make a vertical chart. So here's all our data, and it'll help us if we actually put an order of the lowest to greatest, or vice versa, just to make sure we're going about this the right way. So obviously we'd start with 15, then 18, then 20, 21, and 26. Okay. The next piece of the chart, I'm going to highlight it one step at a time here, will be this, the data minus the mean. So in other words, kind of write it like this, data minus the mean. So what this is we're going to take 15 and subtract from 20. So we'll actually solve it. That value is 5, right? And actually not just 5, but negative 5. 18 subtract 20 will give us our negative 2. 20 subtract 20. Yeah. 21 subtract 20. And 26 subtract 20 will give us 6. Great. So these are actually the values that are technically under here. I just wrote this process out. Okay. So sometimes what we'll write as the next section of the chart would be x minus x bar squared. And if you notice, that's essentially what we have here. Okay. So we're just going to square each of these values. And what you're going to notice is the squaring of it is going to make everything positive. Okay. So negative 5 squared will give us 25. Negative 2 squared will give us our 4. 0 squared is 0. 1 squared is 1. And 6 squared is 36. Now from here, this symbol here, like we talked about, represents the sum of. So we need to sum up all of these values. And once we do that, we'll have the top part of this equation. We'll be able to represent the sum of x minus x bar squared is equal to, and we're going to do that right now by summing up all of these values. Okay, so all of these values, yeah, 25 plus 4 plus 1 plus 36 is 66. Okay, so the sum of all those values is 66. So when we go to fill out this part of the equation, we now have our value for it. Okay, now we also want to divide this 66. So this is 66. Okay, so that's what this part is here. Now I'm going to actually solve just the part underneath. So the next thing is for our variance. Okay, and because this is a sample, it's usually represented as s squared. Our variance is going to be equal to the sum of these values squared divided by n minus 1. Well, what was our n in this case? Yeah. So what are we going to be dividing by? 4. So what value is going to be on top? 66 divided by 4. Okay. So when we get that, 16.5, right? We have 16.5 as our variance. To find the standard deviation, I just represent that with SD, we're going to have to square root those values. Okay, so we need to, I'm going to say the standard deviation is equal to the square root of the variance. Okay, so we'll square root our 16.5. Square root, there it is. 4.06, I guess we'd say. And did I add all those values up properly when we first did it? 9. Yeah, that looks right. Okay, so our standard deviation is 4.06. Great. So that's the important information we have. Now we use that with our z-scores, that formula. So remember our z-scores, a z-score, and we're going to do one for each piece of data. So the very first piece of data we had was the number, yeah, I didn't show it there, 15, yeah. And the formula reads the data, subtract the mean divided by the standard deviation. We need that standard deviation in order to calculate our z-score. Okay, because this was the goal, to calculate the NZ score. So for the first piece of data, that's the number 15. Subtract 20 as our mean, divided by 4.06. And what is that going to be? Negative 5 over 4.06. What did you get?
Negative 1.23.
1.33?
23.
Oh, 23. Great. And that makes sense. We're going to talk about that in a second. Let's do the second Z score. The second Z score was the value number, and I'm just going to quote that there, 18 minus 20 divide 4.06. So that's going to be negative 2 divided by 4.06. And what are we going to get here?
Negative 0.49.
49. Great. The third number was 20. And here's a quick way. Ready? 20 subtract 20 is going to give us 0. And what is 0 divided by 4.06? That's right. We have a z-score of 0. In other words, it's directly on the mean. And z-scores talk about how far we are from the mean. I'll kind of show in a second. The next one was the value of 21, which we know is going to be 1 over 4.06. What did you get?
0.24.
0.24, yep. And finally, 5 was the value of 26. What did you get for that?
1.47.
1.47. Okay, so these are our raw z-scores here. Each of these represent a raw z-score. Negative 1.23, negative 0.49, 0, 0.24, and 1.47. I'm just going to go to 100 here. Now, I'm just going to quickly talk about, you see, these values are negative. And negative z-score values mean that we are less than or to the left of the mean. The mean was 20, so these values, 15 and 18, are to the left of the mean. That's what negative is letting us know. 0 means we're directly on the mean, which makes sense, right? 20 was the mean. We're exactly where the mean should be. And anything positive is discussing kind of how far along we are in the above the mean or to the right of the mean. And the reason I say to the right of the mean, I'm just going to show you the sketch. I know we haven't talked about it, and you're not technically talking about it yet. But you're going to get into something called a normal distribution. And assuming that our sample data here was normally distributed, okay, this would kind of be where our mean is, let's say, our mean of 20. And they start to talk about deviations. And that's what these represent, z-scores. So here's 1 deviation, 2 deviations. And for the most part, we talk about 3 deviations left and right, okay? So just to give you an idea, this would be 1 deviation, this would be 2 deviations, 3, and this would be negative 1, negative 2, and negative 3. So each of these would fall, our first one would fall kind of here at negative 1.23. The next one's at negative 4.5, so that's probably in here because this is the mean. The mean's represented x bar. Our next one would be 0.24, right? And then we have another one at 1.47, okay? Just to give you an idea of what you're about to get into. So that's how you deal with variance and standard deviation.